Streams have started. Information flow. Okay. So I've just started my streams, this time using the Cube and Core Services to start all. And so we should soon have streams appearing on YouTube and Facebook. I'm going to experiment with changing cameras in the middle of my opening remarks, so we need to be a little careful. Today I might make quite a few mistakes. I have to change from this camera to camera 3 after I complete my remark about being in my iTV studio in Cambridge, Massachusetts. And camera 3 at the moment is on my preset 1, which is what I'm looking to do. I'll stay on preset 1 until the end, at which time I'll go to the DS downstream key number 2 and hit the color. And I'll be talking about my different lectures from Monday through Friday, the different topics, and that today we're on the Einstein. Now, while I'm doing that, and this is a challenge, I need to just change my camera 3 preset to 2 so that when I come back up again, I'll be having my whiteboard screen off to my left, to your right. Okay, we're at 2 minutes. I'm going to rewrite this script so that at 3 seconds before the close, I will switch from this key to this key so that I can now fit in my head in this space on the left and talk about the lectures Monday, and so forth, through Friday. I'll just go back to my countdown clock. And I may have messed this one up and run over a little on the time, but as I get done with my opening remarks, I will press downstream key 2, bring the color back, and when I'm done with that, I'll press camera 3, which at that point will have the whiteboard screen up, and that should do it. Oh, camera 3, and then the downstream key off, which is always a trick. When I turn to 3 from this, I get the other look. I go back to that. So I'm going to go to downstream key 1, color 2. I'm back on camera 4, which is my default camera for the opening scene, which shows a small part of my iTV studio. I'd like it to show more, and as we go along, I hope I'll develop techniques to show a few other things besides my new multi-view that I can bring out to the program, and some other camera moves from the back of the studio. So thanks for listening to this short 3 or 4 minute introduction before we go live, and we're going live now in 40 seconds. Probably not necessary to have this blink out, but it might be helpful. Welcome to the Information Philosopher. I'm Bob Doyle, webcasting from my iTV studio in Cambridge, Massachusetts. I'm hoping to reach philosophers and scientists around the world to help solve some great problems in philosophy, in physics, in biology, and in psychology. I also hope to reach any of you wondering about the deep nature of reality and our place in the universe. We live in the information age, but I find that few philosophers or scientists understand the nature of information, an abstract quantity that I will claim is the stuff of our thought. Information is neither matter nor energy. Information needs matter to be embodied in our brains, for example, and it needs energy to be communicated, like this lecture coming to you over the internet. But matter and energy are conserved quantities. It may be hard to believe, but the total amount of matter and energy today in the universe is the same as at the beginning, nearly 14 billion years ago. And if the stuff of the material world is just a fixed total amount, what can possibly explain all the evolutionary change that we see, the amazing new things emerging under the sun? I'll explain those cosmological changes by showing that information and order in the universe have been increasing since the beginning of time, despite the second law of thermodynamics and the increasing entropy which destroys order. Change is simply the arrangement of matter, the atoms and molecules, into what I call information structures, like the galaxies, the stars, and the planets. The stars are passive objects under the complete control of physical forces like gravity, but living things, you and I, are dynamic, growing information structures under our own control. I'm going to show that we are forms through which matter and energy continuously flow, and I'll show its information processing from the DNA in our cells to the thinking in our minds that controls those flows of matter and energy. Information is the modern spirit, the ghost in the machine, the mind in the body. It's our soul, and when we die, it's our information that perishes. Only matter remains. Information philosophy can also explain mysterious aspects of quantum physics, like the two-slit experiment, the collapse of the wave function, and entanglement, which claims a cat can be simultaneously dead and alive, that one object can be in two places at the same time, and that information travels faster than the speed of light. I hope to show with Albert Einstein that such spooky action at a distance is simply impossible. So let me look at downstream key 2, turn some color on. Here we are, reminding me that it's Friday today, so our topic for lecture today will be Albert Einstein. And on our other days, next Monday we'll begin with great problems. Tuesday will be another lecture on free will. On Wednesday we'll be talking about from one or more of the philosophers and scientists on my website. Thursday is metaphysics, and Friday is Albert Einstein. So let's take a look at camera 3, turn the downstream key off, and we come to our larger view of my camera 3 with the Information Philosopher website showing on that screen. I want to remind you that the Information Philosopher is fundamentally the major part of my work that I've done for the past 20 years, transforming 60 years of studying philosophy and scientists into a website. This website is designed to have, on the left-hand side, I'll just enlarge it a little bit, bring this to the right-hand side, and it has, down the left-hand side, a very large number of philosophers. These are the resources that I want to have available to you, and perhaps the half or more of the website is the work on individual thinkers. Each one of these links can take you to a very long page in some cases, especially the Einstein page we're going to look at today. And as you turn to those, I hope you'll learn a great deal about the importance of some philosophers. Now, I also recommend that you go to the Wikipedia pages on a given philosopher from time to time, and that makes a lot of sense. But frequently I find the Wikipedia is now limited to biographical information, where the thinker was educated, and biography, life matters, which are all interesting, but my pages are trying to go to the real central contribution made by an individual thinker. and why they're important today, why they maybe still have the really best idea about how certain problems might be resolved, or if they've made mistakes or taken traditional positions that really were not as clear as we can think of them today. I will be saying so on my pages. So let's go back to this page, and I want to say that the other thing that's on my website, and the best way to see that is to get up another page. I will just quickly put in information philosopher and switch to this screen. I will, and when I have this view, I'm able to show you that there are drop-down menus. Under the introductions section, I've got the creation of information, the physics behind the story, and so forth. And under my knowledge drop-down, this was one of my early works, I'm basically dealing with epistemology, and there I introduce a number of arguments for how it is that we know what we know. Under the value section, this is quite controversial. I'm hoping to argue that there might be an objective value to be found in the universe, independent of humans, independent of a kind of bioethics that's based on life itself on the earth. Instead, it's an objective value against which we can see an objective evil going on out in the universe. My free will section, of course, is the first book that I produced. Let's quickly take a look at that. My Free Will Scandal in Philosophy hope to convince philosophers, academics teaching philosophy to young people that they should not teach that we are just robots, that we are just automatons, that our brains are computers, and that we are machines. I think anyone who thinks that our brain is a computer and that we are machines doesn't know much about the brain, and even less about computers. So that's my arguments in the book are all in these several drop-down menu items. I then have a section on mind, which will become my fifth book. I have just a bare beginning on that book, but many of the arguments will be found in these drop-down menus. Then I'd like to talk a lot about chance. I have not really written much about it yet, but I plan to. And then I have a very long set of pages on quantum physics. And the star of quantum physics in my, as I see it, is not the great founders of quantum physics like Niels Bohr and Werner Heisenberg, Paul Dirac and Pascual Jordan, but Albert Einstein. And we'll be talking about Einstein today. So, and I need to bring this one back to something else, like maybe my right-hand screen. Let's do the left-hand screen for the time being. Okay, so the next important book that I want to tell you about, not complete, but started, and about a third of the chapters have been written. They won't appear yet in print form. My books are available in print form, although they're somewhat expensive for students and those who really around the world don't have, can't afford perhaps to buy print books. So I've taken all my books and put them online on the Information Philosopher website. So let's take a look for that. And it basically, I will go to my menu and I'll type in /books. There's probably another way to get there, but let me do this for the moment. And we are looking at this page, and I can take that page up on the website by clicking on this one. Not quite, not working. So let's stay with this for a moment. Basically, the three books that are complete are Free Will from 2011, my book on the great problems of philosophy and physics, and a bit on biology and psychology that I published late last year, and Metaphysics came out in December of last year. The one I want to focus on right now is that I've written a book on Albert Einstein. And I just see why I can't bring that up on the other screen. Here it is. And let's just click on that link. And we see the cover of the new book, in which I claim that Albert Einstein invented most of quantum mechanics. I wonder if I can zoom this page. No, not really. I would need it on another website. But you see the chapters that are done. The introduction, the story of chance, the story of material, and then a chapter on light, radiation. It's the interaction of radiation with matter that's the main thing that Einstein is going to explain, because it's in the interaction between matter and radiation that chance emerges in the universe. Here's his chapter on deciding that light comes in quanta, which he did in 1905, but it wasn't for 20 more years before Bohr and Heisenberg and the others saw that as related to, but not necessarily identical with their Heisenberg uncertainty principle, for example. So, once again, I've got to get back to something like this. In order to study Einstein, I have, over the last 12, 13 years, bought all of the wonderful volumes of Einstein's works that were published initially under the auspices of the Einstein Library in Jerusalem, who are the owners of all of his manuscripts, and originally in the original German language. But in recent years, they've all been translated into English. I bought all those English volumes. I have a very large library with about 17 volumes on it. And I'm very happy to say that the Einstein estate has decided to put all of those works online. And so I will have links to them at the bottom of my Einstein page. In the past, when I write about a philosopher or a scientist, I take hard-to-find articles or excerpts from books that are not that easy to find, especially for those of you who are just interested in these problems and not working professionally, that you're not an academic and you don't have access to a library like I do at Harvard's Widener Library, which is not just a massive repository of great and important books in philosophy and sciences. It's also giving me permission to go as a faculty member to online copies of scientific articles from almost all the major journals in the world going back to the beginning of their publishing. So that's an enormous privilege, and what I've done is when I find that a subject, a problem is best understood by reading a complete original article, I have put a PDF of that article at the end of the webpage on the particular philosopher or scientist. So what will we do to look into Albert Einstein? Well, like any other philosopher, we would scroll down until we find his name. Let's enlarge this. And these are all philosophers, of course, about almost 200 of them. And we take a while before we get down to scientists. Sorry that this thing is rather slow to scroll. On the main text of this page, I'm describing the various important problems that we deal with in philosophy, and then also a significant number of problems that we deal with in metaphysics. And here we're finally getting into the scientists, so I can come to Albert Einstein on the page and we can take a look at his page. Now, I'd like to just perhaps switch back and show you the the Einstein book, which again is just a draft, but it contains some interesting thinking, and maybe I will just scroll in, if I can here. Yes, I've got to be on 6. I'll zoom in. That's pretty readable. I'd like to take my kind of introductory material on Einstein, which begins with asking a question. Basically, is it possible, and I'm not sure I can bring this up on my other screen, is it possible that the most famous critic of quantum mechanics actually invented most of its fundamentally important concepts? Now, this is really an enormous conceit on the part of any scholar, and so I have, through the years, been nervous about trying to claim that he has done most of the heavy lifting in the subject of quantum mechanics, and yet nobody, or almost no one, pays much attention to his contributions, primarily because he's perceived as a great critic of quantum mechanics. So here's what I'm giving a sort of top-line result. Besides quantizing light energy, so the quantum hypothesis, right, which is thought to be the work of Max Planck, and Max Planck did introduce the quantum constant, the quantum of action, as he called it, in 1900. But when Max Planck did it, he didn't really believe that energy came in quantized amounts. He simply used a mathematical device, a heuristic argument that by putting in quantized amounts of light, he was able to solve for the radiation distribution curve. And we'll explore Max Planck in chapter 4 on light in the book. But first, besides quantizing light energy and seeing its interchangeability with matter, now interchangeability with matter is perhaps the most famous equation ever written in physics. Besides those, Einstein was the first scientist to see many of the most fundamental aspects of quantum physics. The physical derivation of the black-body radiation law, that's Planck's radiation law, and where Planck was able to derive it mathematically, Planck, never really understood it physically. And when Einstein said it depended on the real quantization, that light comes in discrete lumps that are called quanta then, or light quanta, and today called photons, Planck himself denied for at least another 10 years or so that light itself came in lumps. So beyond deriving the Planck law, which was the origin of quantization, Einstein did non-locality and the instantaneous action at a distance, so-called spooky action at a distance, which Einstein will make famous a lot later, but he first saw it. I will try to argue that Einstein first saw action at a distance in 1905. And then a year later, he saw for the first time that there was an internal quantized structure inside matter, inside atoms, in particular inside crystal structures, which had vibrations which were not smooth and continuous at all frequencies. Instead, they had specific frequencies, and that suggested to him, to Einstein, that there was a structure inside matter. And then, 3 years later, Einstein wrote a paper on wave-particle duality, the famous notion that sometimes matter appears as a particle and sometimes it appears as a wave. We'll see that he already saw that it was always both in some sense, that light has a particle quality, he discovered it first, and it has a wave quality, which he knew because traditionally light had been thought to be a wave for a couple of hundred years when he first made this combination, the discovery that there's a dual nature to light. And then the wave nature of light, which is was well understood in 1909, Einstein argued that that wave nature had a strange disappearance at the moment that a particle appears. So we'll say it's called the collapse of the wave function, or the collapse of the wave aspect, I call it here. And when such events occur, they are the emission of a light particle or the absorption of a light particle, many other quantum events. Einstein in 1916 basically calculated the transition probabilities. One of the few times in quantum mechanics he got into the mathematics. He's famous for his great mathematics studies of relativity, but he did little mathematics in quantum mechanics, but he did calculate the probability for emission and absorption processes that are the source for indeterminism, because whenever matter and radiation interact, we get statistical results that cannot be individually predicted perfectly. We can only make predictions probabilistically. That made quantum mechanics into a statistical theory, one that Einstein considered incomplete because we simply have no way to know the exact position and momentum of any particular particle. And that will, 10 years later, after this work on transition probabilities, become the basis for the Heisenberg uncertainty principle. And then in 1925, working from a suggestion made by the Indian physicist Bose, Einstein showed that elementary particles, like an electron, are indistinguishable from one another. And this is a very strange concept which we've only met previously in metaphysical discussions of the principle of identity. When is one thing identical to another thing? Unbelievably almost, Einstein showed that for all practical purposes, every electron is indistinguishable from another electron, to the point where that if you exchange the two of them, it is not like changing physical balls and counting the number of ways you can combine those balls to make an information structure. The interchange of two identical particles does not change the quantum physics, and it led to some very unusual properties in what's called quantum statistics. And then his final kind of coup de grace in 1935 was the famous paper called the Einstein-Podolsky-Rosen paper, after the two physicists at Princeton at the time that helped write the paper, indeed wrote too much of it in Einstein's view, in which they discovered this property of entanglement, that interacting identical particles remain entangled with one another as they separate away. And the question became, could they separate? When do they separate? When do they become independent of one another? This concept of entanglement, when it was first introduced in 1935, it produced a lot of concern. What was Einstein saying? He was at his most critical of quantum mechanics because once again he'd seen a very strange behavior was implied by the quantum physics of the day. But today we can say perhaps that the paper on entanglement in 1935, 80-some years ago, was perhaps the most powerful paper that Einstein had written because it suggested a behavior of reality at the microscopic level which no one could understand. So we can take the Einstein page as our main sort of locus, our main pathway to explaining Einstein, because this page, I'll come back to that here. No, we've got that on the book. So let's go back to my Einstein page here, and we can say that this page at this moment has almost as much material, and in some respects more, than I have in the books, because it goes on to topics that aren't yet written down. I would just like to then look over the time here and start in right at the first paragraph. And I argue that because of that indeterminism that I mentioned, Albert Einstein's work on quantum mechanics, let's see, is really of major importance to the whole idea of information philosophy. Let me go to this. I can't do that. So why is it so important? Because information philosophy depends on the concept of some limited indeterminism in the world. Not that the world is chance ridden or randomness everywhere, but there is a randomness, a chance, or an indeterminism down at the microscopic level. And one of the goals I'm hoping to do is to introduce it into our brains, giving us a random element that I believe contributes to our creative ability. This indeterminism gives us a possibility of an open future, because if we had no randomness whatsoever, if there was no indeterminism breaking causal chains with the past, then everything that we know today would be implicit, that is to say, in principle, knowable by the information that was present in the world in the past. This is the great idea of a Laplacian superintelligence who, if that intelligence could measure the positions and velocities of all the particles in the universe at any time, today or earlier, then that knowledge would give the intelligence, the superintelligence, the ability to calculate the positions of the particles, molecules, atoms, whatever, at any future time. And if everything depends only on the material in the universe and its distribution, then the suggestion is that the world is indeed predetermined from time zero. It is predestined in the religious sense by a picture of the world in which we have a destiny, fate, and that the future is there, and whatever happens in the future will be happening to us. It wouldn't be something that we are making happen. So that's an enormous implication, a large part of my work. So Einstein discovered indeterminism and ontological chance, but here's the sad part. He could never accept them as his final theory. And so all his life we will find Einstein arguing with himself on whether his quantum theory was the final theory. He hoped it would be a theory of quantum fields, it would be a field theory. Toward the end of his life, indeed all the way along, in the meantime, he said perhaps there's nothing in the universe except particles, and that fields are just averages over large numbers of particles. It's a large part of my work to argue that averaging over a large number of quantum particles does a couple of things. First of all, it averages out the randomness. If there's some randomness this way and some that way, it comes out to cancel more or less. And especially in a very large object, there are so many quantum particles that for all intents and purposes, we can regard it as a solid mass and that it's moving according to Newtonian laws, or now that we understand Einstein's theory of relativity and gravitational theory, so general relativity, we can make predictions of the motions of planets, stars, spaceships, which we can launch from Earth and then understand where they're going so accurately they can go to the moon, put astronauts down, pick them, bring them back again. It's amazing how accurate and how powerful is the standard theory of physics is, which when you average over a large number of random microscopic particles, the randomness more or less completely averages out. I should just note that when we send astronauts to the moon or other unmanned rockets to the planets, we're doing it with computers, and computers, while extremely accurate, they are not invulnerable to cosmic rays and other disturbances that can cause errors in them. That's a related problem, not exactly the same problem. How is it that we get to eliminate errors? How is it that we can detect those errors and then have our computers have enough of a backup understanding of what it's doing to correct those errors. It is astonishing how wonderful computers, how wonderfully accurate they've become in recent years, thanks to their error detection and correction schemes. But biology has had error detection and correction in it for a lot longer than computers, and in many respects it's phenomenally accurate as well, and has a lot to do with what we'll be seeing about the role of quantum randomness and being averaged over, and then if it can't be averaged over and it destroys, for example, a little piece of our DNA code and makes a mutation in our species, we can see how the error detection and correction mechanism works as every single protein enzyme is created in a ribosome. I think Einstein would have liked that very much. But coming back to him, it's my goal to show that in the 2 decades before quantum mechanics was founded by these great guys, Werner Heisenberg, Max Born, Pascual Jordan, Paul Dirac, Erwin Schrödinger of the famous Schrödinger cat that's dead and alive at the same time, as we mentioned in our opening. We will show that Einstein had discovered ontological chance fully 2 decades before the quantum mechanical founders, I should say, 1 complete decade, so in 1916. But I'm going to show that if we had no chance, we'd have no information. Without chance and new information, there can be no free creations of the human mind. This free creations of the human mind is a wonderful quote from Einstein, which I think I can show that he actually read it in the work of a great mathematician, Dedekind. And the two of them are more or less mathematical physicists who believed at the time in determinism. So it's interesting to me that I find this wonderful phrase in Einstein: if the universe is completely determined, why would he add free creations of the human mind? Why not just say determined creations of the human mind? So that we could have had an Einstein who did what he did because he went through life believing he was part of a rational universe in which there were explanations for everything, even though he might not know them. We might not know what those explanations are. A fully deterministic mathematical universe would contain the causes which led to a not a free but a determined universe. Instead, he calls it free creations of the human mind, and he correctly recognized that that's what he was doing when he was coming up with his new scientific theories. Accepting the humility, or being humble enough to not want to take too much credit for his work itself, but just to put the work out there. Nevertheless, we can see much of the time he really appreciated how lucky he was to be there at the right time to get the basic ideas of quantum physics. Now, although he was a great mathematical physicist, he was not one of those who think that the theories control the world, although he was famous for saying something like that, the great phrase, well, if the experiments don't agree with the theories, so much the worse for the experiments, because he hoped that better experiments would agree with theories. He did give them primacy. But Einstein knew very well that experimental confirmation of quantum mechanics is extraordinary. And in it, the confirmation shows more deeply than anything else that quantum physics is a probabilistic theory, a statistical theory. The equations of quantum mechanics are not equations that are deterministic, although the Schrödinger equation, which will become our most important equation, the one we study and use to make predictions, what the deterministic Schrödinger equation, a function of time that evolves through space and time, is only telling us the probability that particles will be found at any particular space and at any particular time. So Paradoxically, I say, ironically perhaps, and in some deep sense tragically, only a handful of scientists and philosophers recognize the full range of Einstein's contributions. And the reason for that is rather understandable. He basically attacked his own quantum discoveries. Throughout his life, he really just found them extremely difficult to embrace. Many other scientists might have just put the notes in a drawer and gone on with their other earlier work rather than put something out there that they so violently opposed in some sense. And the reason that that we should regard this as a tragedy is because his quantum discoveries were totally contrary to his fundamental beliefs about the workings of the universe. And those are probably best summarized by this great phrase, which he used many, many times. And I want to just then reiterate that that's the reason I chose this title. I thought initially I might write several chapters in this book explaining how, or imagining, an Einstein that accepted the basic notion of chance, that there was ontological chance, we call it, fundamental metaphysical chance in the universe. And I went away from that because it required me to elaborate a lot of ideas about an alternative imaginary Einstein. But what we are going to do is to say that, and those are my grandchildren jumping around on the second floor of my studio, which is not as sound isolated and vibration isolated as it might be. I'm going to show that Einstein did this, and it might have been, it certainly might have been, that his belief about the world, the belief about how we fit in the world, our lives and society, which is a very difficult time for Albert Einstein, before the World War I through to the horrible World War II and the aftermath. I can see why he disliked any kind of disorder. The same thing was in the mind of Thomas Hobbes, who lived in a time of horrible civil disorder. And so Einstein argued, what we need is a Leviathan. We need a dictator. We need a monarch. We need a king. We need someone to whom we give all the responsibility for everything that happens. And that he imagines to be part of a totally determined universe. Free will led to people fighting one another in terrible ways, and Einstein lived through similar times. It turns out there's a second issue that Einstein was worried about, and that's randomness. Not only randomness, because randomness, certainly in his later years, may not have been his primary concern, his main concern. We will see. It's that quantum mechanics appears to conflict with Einstein's own special relativity. And in particular, its non-locality, the idea that there are effects that are extending out to other parts of space, which are not causally accessible is the way to think about it. Things happening in another part of space should not have a causal relation. Imagine, Einstein thinks that, and a Newtonian world too, that the way things happen is that something comes along and bumps something, and the effect is one of contact. Now, Newton had already pointed out that the planets can exert forces and causal forces on one another so that they orbit one another, and they are doing that at a distance. So that was called action at a distance. However, Einstein showed that Newton's work was all consistent with signaling in the form of a gravitational wave, which Einstein predicted waves back in the 80, 90 years ago that have only been discovered in the past couple of years with our great gravitational wave observatories. But in any case, coming back to Newton, his action at a distance was equally a scandal to the thinkers of the day, because they thought that all all forces are transmitted by contact of matter with itself and so forth. And that the idea that there's this strange gravitational inverse square law force of Newton acting through space with nothing in between. There were theories that maybe things were traveling between these gravitating objects, and today we think of that as possibly gravitons, analogous to photons, that are sort of carrying the gravitational force. But that's rather abstract. Not too many people, we've made little progress understanding that possibility. But now what Einstein was confronting in his non-locality, and we'll have some diagrams and animations to show what he was worried about, the notion is that when a particle is discovered here, in, say, the two-slit experiment, which we'll come to, when it's discovered here, instantaneously something changes a distance away. And this isn't a question of something traveling, like something here generates a wave like that propagates through space at the speed of light. No such thing. Einstein basically has to have a situation where when something happens here, instantly another particle or some function like the wave function associated with the particle changes instantly. We will deal with that problem in some depth in future lectures and show you how Einstein saw this thing that disturbed him, but in some sense he never did reconcile himself with this implication of a non-local process, that things happen here that don't depend only on the place where it's happening. Instead, they depend on distant places. That's called non-locality, and we will come back to it. Particularly when Einstein had a field theory, his famous last work, a unified field theory, we had a situation. Let's see, I need to move this up a little bit so you can see. No, you're not seeing that page. Let's go back to this one. The unified field theory demanded that all causal effects are local. They happen instantly and in a local point in space and time. Field theories are point theories. They give the values of all important functions at a single point, and they're said to depend on that particular point in space and time. So, with 15 minutes to go, I'd like to give you a little flavor of where we're going to end up with Einstein. It may be many, many weeks from now before we work through all of the chapters of my book on Einstein and quantum mechanics. But along the way, I will try to give you other important elements to show how his work fit in with other things. And perhaps the most dramatic of the things that Einstein did, as I mentioned in the opening, is that he discovered or argued that there was something he called spooky action at a distance, or spukhafte Fernwirkungen in German. Really, spooky is the word. So what I have here, I'm going to try to go to, let's see, I want to go to this page, and I want to restart an animation. So we'll read along with it. It says that electrons are prepared in a singlet spin state. If you know about entanglement, you probably have the general idea that two things come together or are started off in the center of our experiment, and then the wave function for these two particles radiates out spherically in all directions. And when they get to a very great distance, we have two observers called Alice and Bob, or in my diagram here, A and B. And when Alice makes a measurement on the one electron coming her way, Bob can make a measurement and always finds that the total spin of up and down, electrons are produced with an up and a down, perfectly preserve the total spin angular momentum with those two little arrows as 0. The up exactly cancels the down. I'm going to get another page over here. I'm going to go find this same material because I'd like to be able to put my own mouse down over this experiment. So let's see, I'm right about here, and we can try this one. Here we are looking at the same experiment on another page. We'll take a few minutes here to work through the implications. It says that electrons are prepared in a singlet spin state with total spin equals 0. So the arrows represent the spin, and the up arrow is spinning in one direction, and the down arrow that Bob measures over on this side is spinning in the down direction. So when one electron is measured with its spin up, the two-particle wave function collapses instantly, and the other action is instantly spin down, or minus 1/2. Now, this gave Einstein the problem that, I think another paragraph comes up here in a minute, to compare this to a single particle. Well, we're not going to do that now, but we'll teach the two-slit experiment at some future time. Let's home in on what's the problem here. Why does this seem to be impossible? And let's remind ourselves that the experiments prove this to be the case at all times. Okay? What we have here is an experiment that always shows that the two particles come out in opposite directions in this particular experiment. The two start in the middle and radiate off in various directions. As soon as Alice measures, Bob gets the exact opposite result to preserve the total momentum. This Einstein recognized was what's called the conservation of angular momentum. The great conservation principles of physics say that total mass is conserved, total energy and mass together are conserved, that angular momentum is conserved, and conservation principles are really basic principles of physics, and they're definitely at work here. So let me now scroll down and draw another animation which can kind of give us the picture of what it is that physicists today think about this experiment. Here what I've done is to try to show in an animation that at the center of the experiment, when the two particles are generated, one goes up and one goes down, but on the way as they're traveling, the standard argument, the case to be made for entanglement and the mystery of entanglement, is that we don't know along the way as they travel whether these particles are up or down. Let me show you my animation of that problem. And let's see if I can do it again. You can see I'm sort of animating with the idea that they're in a combination of up and down states as they travel. But as soon as they hit the end, and you know what, I can actually move this slowly. As soon as they hit the end, they are exactly matching. Now, what this animation I'm trying to show you is the notion that if one is in a combination of up and down, let's go in the middle here somewhere. Let's suppose we're here, and that one is in a combination of up and down. I'm using time to show that, well, it may be going up and down, but the other one is doing exactly the opposite thing in order to conserve the total momentum. And this is one way of looking at most of the descriptions you'll read in the textbooks, although I haven't found one that tries to explain it as having an unknown probabilistic value for the spin between the origin, where they set off in two directions, and the final result. When one measurement occurs and the other measurement is measured either at the same moment or a little later, it always exactly matches. So what we're going to learn when we get a long way into this is to see that there's another possibility, and that is Albert Einstein's view that where quantum mechanics says we only have statistical information about the particles as they're traveling apart, and that is complete information, and that's all we can know, that we can't know more about that until we make a measurement, and only when we make a measurement has some information come into the world. Einstein had this alternate view in which he said, no, in his view, isn't it possible that quantum mechanics is incomplete? It was his term. It's incomplete because it's statistical, and the fact that it gives you only statistical evidence about what the particle is doing on the way towards Alice is a simple consequence of everything, from the fact that everything we know comes from many, many experiments. Okay? We're talking about thousands of experiments, and as we do them all, the particles are found up or down, and it usually comes out 50%, and we do not know anything about an individual experiment, an individual electron. All we know, Einstein is saying, is that we have statistical knowledge about that electron, which is to say it might be up or down, and the math of quantum mechanics is to say that it is up and down, both with a probability for each. This got translated by Erwin Schrödinger into the notion that a cat might be living and dead at the same time if he set up an appropriate experiment, and in the experiment a nuclear event, a random event occurs, which we cannot say when that is going to occur. Let's say it's likely to occur once in a day, if it does occur with that 50% chance in a day, it will kill the cat. And so we'll, with Einstein, say, we really don't know what's going to happen, but we can say that it's in a combination, a so-called superposition of up or down in the case of the electrons, or of dead and alive in the case of the cat. Now, most all of us, if we look at this at all with a little bit of a skeptical notion, we never see a cat that is dead and alive. It makes absolutely no sense. The fact that doing many experiments, we find equal numbers of cats dead and alive only tells us that we don't know anything about any individual cat. Now we could say, well, it seems most reasonable that any particular cat is either dead, or let's say is either alive, if that killing cyanide bottle breaking in Schrodinger's horrible experiment hasn't broken, the cat is alive, and that when it happens, set off by a random quantum event, after that, the cat will be dead. Now, taking that back to our picture of the electrons moving apart, Einstein said, what if there's an objective reality, and in fact, any given particle always has the value it has at the beginning? And when a particle heads off towards Alice and is found to be up, and the other particle, which of course must be down, heads off to Bob, it may have an objective reality, is what Einstein called it, of being down. If so, we will basically be able to draw a different picture, one that I will propose might have been Einstein's idea. So let's play this animation. What we see is that when the particles start off, one is up and one is down. Okay, let me just see if it goes again from this. Exactly. The one headed to Alice is up, the one headed to Bob is down. They are randomly up or down at the beginning of the experiment, but then at the end of the experiment, they are what they are. They are exactly correlated with one another. not because some mysterious signal went from one to the other, that the Alice experiment influenced or sent information over here to Bob's experiment. There is no need to send information from Alice to Bob if, while they are traveling from the center, they never are in a superposition, but they are simply in a state that we do not know. So it's what philosophers called epistemic ignorance. And the particles themselves are doing something which is random, of course, but it isn't randomly changing at all times. Let me scroll back a minute and show you what this looks like. To say that the particle is actually changing from up to down very quickly. So when I do it slowly, you see it changing. When I do it in real time, it's changing up and down. The question then becomes for Einstein, how can this particle change its spin from up to down? Where does the power, the cause, the information now come from that allows it to change from one to the other? Conservation of energy, and in this case conservation of spin, suggests that the particle separating from the middle is always up for one, down for the other, and there's no need for any information to travel from one to the other. So, coming back to Einstein, that is my very deep interpretation of his notion of an objective reality. And if it is possible to interpret it that way, I hope I'll find some physicists who will criticize what I'm arguing for, and maybe I'll be shown to be wrong. My wife Holly is very skeptical about this point of view, but I have great hopes that it will be something we can use to explain the mystery of entanglement. Let me go back here for a moment. And so I will at some point be engaging in a discussion of entanglement and find our way out of the Einstein-Podolsky-Rosen paradox. So our program is running out of time. This has been my lecture on, let's see if I can bring this up and put us over to the quote page. And this has been our Friday lecture on Albert Einstein. Let me color those with a nice yellow popping out a key on our screen. And this is actually the last of my practice lectures, which are going out to YouTube and to Facebook, but they are lectures that I would like to begin next Monday formally. I'm just going to bring up my clock here, which got timed out on us. And so next Monday, it will be the first lecture that I will regard as seriously happening, and as opposed to these practice sessions where I'm still learning the ins and outs of my switcher. We'll start on Monday with great problems, and I'm pleased to announce that on Monday, the local public access station in Cambridge, CCTV, has invited me to send my lectures not only to YouTube pages and my Facebook page, but also to send them to their station, where it will be put out over the Channel 9 Live for CCTV in Cambridge. So until then, next Monday, I hope I'll see you. This is Bob Doyle, and I'm the information philosopher. Bye-bye.